So now let us come to the general expression for a specific heat of an ideal gas. So molar specific heat of an ideal gas for a general process. So if I don't know the process, then how I will write this for a general process. So now you see here, we will write dq is equal to du plus dw from first law. So this is from first law. So it's a general process, so it will be NCDT. Whatever may be the process, du is equal to NCV dt. And for configurational work done, this is PdV. Other types of work done will be also there. That is not, so delta W is here, configurational work done. So we will have C is equal to CV plus P by N dV by dt. So for a different process, for different processes, dV by dt is going to be different. So we have C as different values for different processes. So for general process, I will write C is equal to CV plus P by N dV by dt. So now we are talking about this expression for a general process. So generally, for a general process, we use the expression polytropic process. So for a polytropic process, P v to the power n is constant. So this n and this n is different. This n is general n, and let us write this. So we will use nu. So Pv to the power n is constant. So now, so from ideal gas equation, we have Pv is equal to nRT. So let us write Pv is equal to nu RT, number of moles as nu, so that this n and this n should not mix up. So this is Pv is equal to nu RT, where nu is the number of moles and this n is the power. So here we will put this P here, we will get P is equal to, we have C by V to the power n into V is equal to nu RT, which is again CV to the power 1 minus n is equal to nu RT. So in order to use this expression, I must know dV by dt. So we will take the differential C times 1 minus n into V minus 1, that is minus n. This is dV by dt is equal to nu R. So now you see here, we will use this expression and we'll put here. Remember, we will replace this n by nu. So we have C is equal to CV plus P by nu, because n in previous discussion we took n is number of moles. Here nu I have replaced this. So nu by dV by dt is nu R by C 1 minus n V to the power minus n. So C is equal to CV plus P. You see P is equal to C V to the power n, nu cancel, C by V to the power n R upon C 1 minus n into V to the power minus n. So this C cancel, V to the power n minus n. So it becomes CV plus R by 1 minus n. So if we have a general process that is generally represented by Pv to the power n is equal to C, we call this process as polytropic process, then C will be CV plus R by 1 minus n. This is a general formula that is very useful for problem solving purpose. So now let us take an example where we will calculate the specific heat of gases for different processes. So take up few processes. So this is PT process, pressure versus temperature, and you see we have moved from A to B like this. So this line passes through the origin. This is one process, number one process. Next, VT process. So again my process is from A to B. So during this process, I want to calculate what are the specific heat, molar specific heat for different processes. This is PV, and again here the graph is like this. So we have three cases, three different processes, and let us calculate the specific heat for all the three processes. So we start from the first. So here pressure is directly proportional to temperature. You can see this linear dependence. So pressure is directly proportional to temperature. This is possible if volume is constant. That means this process is isochoric process. This process is thus first is isochoric process for which C is equal to CV. So C is equal to CV is for this process. Now come to second process. So again PV is equal to nRT. So here volume is directly proportional to temperature. This is possible if P is constant. So this process is isobaric. So C is equal to Cp. Now come to this process. So here PV is equal to nRT, and you can see P is proportional to V. So P is proportional to V. That means here this P is equal to KV is the process. So here the process is P is equal to KV. We didn't have any simple process like isobaric, isochoric. Pressure is proportional to K. This is the process. So now let us see this third one, how to calculate the specific heat for the third one. So now P is equal to given as KV, number 1 point, and we know that PV is equal to nRT. So what we do, we will calculate V and T. We will eliminate P by KV square is equal to nRT. We put P value here KV. So this is. So now 2 KV dV by dt is equal to nR. This is temperature. Implies dV by dt is equal to nR by 2 kV. So now you see kV is equal to P. I can again write this as 2P. So this is my first relation. Now we use the expression for specific heat for a general process, that is C is equal to CV plus P by N dV by dt. So for this process CV is CV, P by N, and we have dV by dt as nR by 2P. So this P cancel, this N cancel. So C is equal to CV plus R by 2. So this is the specific heat for this process. So you see, in different examples we have seen that how C will depend on the process. There are infinite number of processes, so there is infinite values of C for an ideal gas. Let us take another example. So here we have a gaseous system which is under a piston. So in this gas system I have given Q by 2, Q amount of energy, and as a result the piston expands, and we have observed that it does work equal to Q by 2. So it uses 50% of energy as internal energy, and remaining 50% it uses as heat. So Q amount Q amount of heat is given to a gaseous system in which it performs a work of Q by 2. Find the molar specific heat for such a process. So we have to find the molar specific heat. If we are interested, we can assume monoatomic gas inside it. Suppose it is monoatomic gas. So its CV is now known. So you see here, the first law tells that delta Q is equal to delta U plus delta W. So it is given as Q, delta U, and it is given as Q by 2, implies delta U is equal to Q by 2. Thus we see that delta U is equal to delta W is equal to Q by 2. Now you see, let us write the relation between delta U and delta W. This is number of moles N CV dt. That is equal to P dV. So for a monoatomic gas, we know that CV is equal to, for a monoatomic gas CV is equal to 3R by 2. So we have N3R by 2 dt is equal to P dV. dV by dt is equal to 3NR by 2P. Now let us recall the general expression for the specific heat of a system. So we have expression C is equal to CV plus P by N times dV by dt. So we have C for monoatomic 3R by 2 is the CV plus P by N. For this process we got dV by dt as 3NR by 2P. So this P cancel, this cancel, we have 3R by 2 plus 3R by 2, so that is 3R. So we see that if a monoatomic gas uses 50% of energy into heat and remaining 50 into work, then a specific heat becomes 3R. So we have seen one more example where different processes will have a specific heat, different values. Now let us take an example of a process in which the specific heat may be 0. Now let us take another example, example 3. An ideal gas in which Cp by Cv is gamma, we will explain later on, this ratio is presently called it gamma, is taken through a process in which the pressure and the volume varies as P is equal to A V to the power B. Find the value of B for which the specific heat capacity in the process is 0. So we have to find when the specific heat, molar specific heat becomes 0. So we will use our general expression. So first let us relate how volume changes with temperature for this. So we have P is equal to A V to the power B and PV is equal to nRT from ideal gas. So this is the equation of state for this process and this is the general equation for this PV is equal to nRT. Let us substitute here. So implies from these two we will substitute A V to the power B and this, so V B plus 1 is equal to nRT. Now we will differentiate this here. So A B plus 1 to the power B that is n minus 1 dV by dt is equal to nRT, implies dV by dt is equal to number of moles nRT, number of moles n by A B plus 1 to the power V to the power B. This is how V varies with T, dV by dt. Now, we have the expression C is equal to Cv plus P by N dV by dt for a general process. So, we have Cv as Cp, Cv is R by gamma minus 1 for an ideal gas. Cv is R by gamma minus 1. This is a general expression. We will prove it later on. But presently I am using this formula that Cv is equal to R by gamma minus 1, where gamma is Cp by Cv. So, still I have not proved it, but let us use it. Let us believe it is correct. So, P is A V to the power B by number of moles. dV by dt we will substitute from here. So, that is N R T upon A B plus 1 V to the power B. So, this cancels out, this also cancels out, N cancels out. So, we have R by gamma minus 1 plus, if I differentiate it here, T won't be there. So, T won't be there. So, here T won't be there. So, simply I will get R by 1 plus B. Now, it is said that under what conditions, what is the value of B for which the specific heat is 0. So, this is equal to 0 according to question. So, we have now, if this is equal to 0, we have R by gamma minus 1 is equal to minus R by 1 plus B. Implies gamma minus 1 is equal to minus 1 minus B. Implies we want B. This B is minus gamma. So, if B is equal to minus gamma, gamma is the specific heat Cp by Cv ratio, then this, for this process, the molar specific heat of the gas will be 0. So, no temperature will be raised if the heat is given to the system.